All right, welcome back to CS 2810 Lecture 4. So, just to let you know, in the last class, I had some slides with some mistakes, and I fixed them already. So, make sure you go and download the latest slide. Okay, so we're going to continue with solving the linear system today. So, in traditional textbooks, okay, first I'm going to have a notation update, which I think was the notation from last class was causing some confusion. So, in normal textbooks and how I was taught, the notation when you're combining equation one and equation two, you're subtracting equation one and equation two, it looks like this. But I noticed that it was this notation was causing some confusion. So going forward, I think we should use a different notation. So instead, we're going to say equation one subtract equation two, and that's going to become the new equation one. Okay, so over here, they're going to subtract each other. Just 0, 0, 2. Okay, and this is now going to become equation one. So the addition is basically this. This allows you to know like how equations will combine and then which row it replaces. So that's the new syntax. Also, if you are writing these kind of augmented matrix, right, in LaTeX, the syntax is like this. Okay, you want to use array, left and right creates this, and the array gives you this is two numbers, and then this one right here has a so it says that it's two numbers slash and the third number. That's what this means here. Okay, so let's with that out of the way, let's continue. So last time we learned Gaussian elimination, okay, in the last lecture. A linear system may not actually always have a unique solution. In fact, there are three possible cases. A good unique solution, that's case one, which is what we learn. We learn like the simplest situation where you are able to get a solution. In case number two, a solution is not possible. There's some kind of contradiction. And case number three is when you have infinite solutions. Now, given this, right, take out a piece of paper now, pause the video, and see if you could figure out which case this one is. Okay? Well, all right, pause the video because I'm going to move on. All right. So, a linear system that is not possible. This is a linear system that is not possible. And let's start by converting this into the augmented matrix. Once we convert it into the augmented matrix, I'm going to do 2e1 minus e2 and make that the new e2. So, okay, if we do that, the new e2 will look like this. If you do this, well, I want to show you that if you convert this back into an equation, and then the equation will look like this. What's happening is that it's saying that 0x1, 0x2 is equal to 1. Or it's saying that 0 is equal to 1, which is a contradiction. So this is not possible. So whenever you're manipulating the equations, if you somehow get a row with all zeros, and if this is not a 0, that means you have a 0 equal to some number, causing a contradiction, and that means a solution is not possible. There's a contradiction. Or let's see. Yeah, it's not possible. Okay, let's now look at yet another example. Okay, in this example, if you were to take so this is already 1, so we can take 1 to get rid of these to make them all zeros. If you were to make them all zeros, essentially you have minus 2e1, okay, minus 2, and you subtract e2. So you're going to subtract this away. And we're going to make that the new E2. And then we're going to do again minus 2E1. And then with this time, we're going to subtract E3 and make that the new E3. So we're going to replace essentially both of them. Once we've done that, the new equation looks like this. At this point, I can do 4 over 5 times E2 and add that to E3. And now we're going to get a 0 over 0. 0 equals 0. In this case, we have also reduced it to something really simple. But 0 equals to 0 is not a contradiction. So it's okay. And you can continue. Over here, in fact, if you continue, you're able to find x1 and x2. Remember, we have 3 equations with 2 unknowns. All you really need is 2 equations. So if one of them is not useful, that's okay. You can still go on and find x1 and x2. A contradiction only happens in cases if you end up getting like 5 equals to 2. That's a contradiction. Or you end up getting an equation where you have 2x1 equals to 2, 2x1 equals to 3. Obviously, 2x1 cannot simultaneously equal to 2 and 3. So that's a contradiction. So those are the cases you want to look out for. Okay, now notice the key difference between the two cases. In one case, right, there's a statement that says 0 over 0. No contradiction there. In another case, 0 equals minus 1. You can't have that, right? So as soon as you have a contradiction, it means that you can't really have a solution that satisfies all the equations. Okay, in this example, now we have infinite solutions. Okay, infinite solutions. This is the case when you have more unknowns than the number of equations you have. So if you have, like, over here is 4 unknowns, and then you have 2 equations. So that's not enough. So you don't have enough information to really pin down all the variables. In those cases, when you reduce them to the lowest echelon form, you're going to get these variables to the farthest left. They are called pivot or leading variables. So x and y are leading variables because, well, they're leading other variables. And the rest of them, z and w, they're called free variables. So the idea is, once, because they're free, you can set them to any value. But once you set them to some kind of value, right? Imagine if you set them to some kind of value, you don't have a choice now. You have to have some kind of y that depends on z and w. And since y is dependent on z and w, now we have y, z, w. So x is dependent. So as soon as the free variables are chosen, which you can pick anything you want because you don't have enough equations to pin them down. So if you pick any free variable you want, then the pivot variables are kind of stuck. They have to follow the free variables. In these cases, when you don't have enough equations, you're going to end up with infinite solutions. Here's another example I can show you. In this case, the leading variables are x2 and x4, okay? And the pivot, they're the leading and the pivot variables. And the free variables are x3, x5, okay? Once you pick x5, you have no choice. You automatically have to know x4. So more examples, leading versus free. Over here, notice that we have the leading variable x1, x2, x4. And these ones are the free variables, x3 and x5. Okay. Now, notice, let's say, remember x3, x5, those are the free variables. Notice that if you pick x3 and x5, equals to 0. So if this is 0, you have no choice anymore. The leading variable, this has to be a 0, right? It has to be a 0. And if you know that x3 is 0, x5 is 0, and now we know x4 is also 0 because we just learned that from here. So we now know what x2 is. And then consequently, we know what x1 is. Okay? That's the point of free and leading variables. Okay, let's see how they are solved. Given a linear system of equations, okay, we first step one, we first convert it into augment the matrix. So here's a linear system equations. So the first thing we do is we convert it into augment the matrix. After that, we find the reduced row echelon form. Okay. Now it's reduced row echelon form because it's diagonal. Even though we are missing a couple of them, they're all zeros. As you want to make sure it's diagonal and the leading variable above all the leading variables are 0. Okay. So now this is the reduced row echelon form with infinite solutions. That's what it will look like. Now, once we have reduced row echelon form, notice that there are no contradictions so far. 0 equals to 0, it's okay. So no contradictions. And we have a nice diagonal, although it doesn't go all the way down, but we have it set up as a diagonal anyways, with 1s as the pivot and the leading variable. Now, yeah, like right here, the x1, x2 is leading, x3, x4 is free variable. What we do now, once we're in this state, is that we convert this back into equations. Okay, so now we have essentially two equations. So this goes here, x1, 1, and then 2, x3, 2, minus 2, x4. So that's where this is. And the 2 goes here. Okay. And so once you convert both equations here, what we want to do next is that we want to represent the solution. So this is the reduced row echelon form. We don't have like the nice form, but we can now have a way of represent infinite number of solutions. And the way you do that is you represent every variable, okay, in terms of the free variable. What does that mean? You represent every variable in terms of free variable. Okay, so x1, right? How do we represent x1 in terms of the free variable? Well, x3 and x4 are the free variables. So why don't I just move this here and this here? So x1 is 2, right? 2 minus 2x3 and then plus 2x4 right here. Okay? So that's what I mean. That x1, now you're representing it in terms of free variables. And now you have x2. What is x2? x2 is equal to minus 1 plus x3 minus x4 right here. Next, how do we represent x3? Well, we're going to represent x3 with a free variable. So x3 is already a free variable. And then x4 is also a free variable. So once we convert it back, we represent the solution in terms of free variables. Okay? And then we convert this, rewrite this into a matrix format. So notice we can pull this out into 1, x3, x4, right? 1, x3, x4. If we multiply this with this, notice it's just the same thing. And now we have the solution. This right here is the solution. Basically, you can pick any, and I mean any, x3, x4, plug it into this. So this is the equation to generate solutions for this problem. Okay? So because there are infinite number of solutions, we can just always generate different kinds. And it's generated by randomly picking x3 and x4. Okay. Now, this is right here. Remember, this is the solution right here. I'm copying that over here. So this is the solution. And I just told you, and this is the original problem, if you remember. Solution, original problem. So I told you, given any free variable, z and w. Oh, I made a mistake. Over here is x3, x4. Over here I call zw, but the idea is the same, right? X, Y, Z, W, X1, X2, X3, X4. So the idea is the same. I think I had a typo here. But anyways, they're basically the same idea, just different symbols. So anyways, I told you that we can plug any of these two in. So let's randomly pick something. Let's just make them 0. That should be a pretty easy case. So if you make this 0, we can now generate a solution by plugging this and multiplying by this matrix. Now, if we multiply them together, we're going to get this right here. So this is a dot product. Basically, everything's going to be 0 here, and it will be this copy here. So that's what happens if you have the dot product. Okay? So this is a solution to this. Okay? Let's see if it's true. Okay? Let's plug 2 minus 1, 0, 0. 2 minus 1, 0, 0. Okay? We'll plug that in. And then we'll plug this in again. 2, there isn't a term here, so that's 0. Minus 1, 0, 0. And then 2, there isn't a term here, right? So this is 0. 2, no minus 1, 0, 0. And then nothing here, minus 1, 0, 0. So what I did, essentially, is I plugged them into each one of these variables. And you can verify yourself that 2 minus 1 is just 1. Minus 1 is just minus 1. 3 times 2 is just 6. And minus 1 is 1. Therefore, this is true and very good. So we just plugged Z and W in here as 0, 0. And like I said, I picked out randomly. Let's pick another one. If we can pick anything and it'll work. Now I'm going to pick 0, negative 1. So something else. If I pick 0, negative 1, then let's see. Did I have I have a typo. This is supposed to be minus 1. Okay. So if we do minus 1 here, let's see. When we do the dot product, this and this will cancel out. This and this will cancel out. That's how we got 0. And then we multiply this and this. That gives us 0 again. And the very last one gives us minus 1. So the minus is there. Okay. Let's see. So this is our solution now. Remember, we randomly generated Z and W. You give us one possible solution. Now we put in another one. Z and W equals minus 1. And you give us another solution. And what I'm saying is, if we plug this solution in here again, it's going to be fine. Okay? So over here, essentially you just plug negative 1 into the last term. And you will see that minus 1 is 1, minus 1 is minus 1, minus 6 minus 1 is 6, minus 1 is 1. So again, it matches the solution perfectly. This right here is a solution. This right here is a solution. Essentially, you can pick any Z, any W, and then it allows you to generate a solution. Once you have a solution, if you plug it in, then you're always going to get this result. Okay? So this is the case where you have infinite solutions. Okay. Now, you want to essentially pause the video and then give this a try. Right? Here's another example, I think, with infinite solutions. Okay. Pause the video because I'm moving on. So over here, well, the idea is pretty simple. We take this, make it into augment the matrix, and then I start reducing until in the very end, I have the reduced row echelon form right here. Now you can you want to make sure you follow this along, like follow along, so you know how we essentially got this. But we did that last class. You should know by now how to achieve the reduced row echelon form. Okay, so that's first thing we did. Okay, now once we have this, remember first thing is we turn it back into equations. Rewrite them in terms of the free variable. Once you have the free variables, you simply need to represent them again in the matrix vector format. And that's it. This is the solution. And this is how you can have infinite number of solutions. Okay? Now, if you were to solve a singular matrix, I forgot to mention this. If the problem, right, this matrix here, right, from the augmented matrix leads to infinite solution, then this matrix is called singular. Okay. Anyways, singular is when you have infinite solutions. So what I'm saying is when you try to solve a singular with numpy, it's going to crash, right? So I think I plugged this in here into numpy, and I try to solve it, and it causes a crash. Similarly, if there's no solution, it will also cause a crash in NumPy. Okay? Crash. So in this case, you see it's saying that 0 is equal to -1. Okay? NumPy can't solve it because there isn't a solution. However, you can identify matrices with no solution using SymPy with the RREF function. So the RREF will essentially give you the reduced row echelon form. Once you have that, you can look for contradiction. Notice over here, the entire row is 0, but it's equal to 1. So that's a contradiction, right? So you can identify no solution problems through SymPy by looking at the reduced row echelon form. You can also identify matrix with infinite solutions in SymPy. Okay. Now, over here, you can tell that these two are the leading variables, and these two are the free variables. So, because there isn't a nice diagonal 1 and 0 everywhere, you can tell that this has infinite solutions, and therefore the matrix is singular. This is singular. Now, remember last time when we were solving SymPy, this right here, we plug 0. This means that whatever this function was doing is returning more than one value, and we're taking the 0th value. The 0th value gives you the reduced row echelon form. But what is the first value? The first value tells you the location of the leading variables. So since this is programming, it starts counting from 0, 1, 2, 3. So the leading variable is 0 and 2. See that? Those are the leading variables. So therefore, with SymPy, you can get the leading variables as well as the reduced row echelon form. And if you have the leading variables, that's not all of them. that tells you you have number of infinite number of solutions. Okay, now we have three shapes of a matrix. Remember, square, tall, fat. Depending on the size, so if you have a square matrix, it is possible to have a unique solution. No solution, infinite solution. Similarly, if you have a tall matrix, okay? But if you have a fat matrix, that's the case when you have more unknowns than equations. That's a fat matrix, and that's when you have either no solution, infinite solution. When you have a fat matrix, um, it's it's um, it's impossible to have a unique solution. Unique solution. That's not possible. Now, when we're talking about these matrix, okay, we're talking about, remember the augmented matrix? 1, 1, 2, 1. Okay, we're talking about this portion here. This is the matrix we're talking about. That is singular, tall, fat, square. Okay, if this is, like I said, a fat matrix, then it is impossible to have a unique solution. Now, these linear system solutions actually has a geometric meaning. So we know that this is a line. Okay, let's say x is equal to 2. This means y has equals to 0. Okay, so x equals to 2, y equal to 0. Again, if we have y equals to 2, then x has to equal to 0. So this right here essentially represents this line, the blue line. And the other equation essentially represents this. Therefore, xy, everything along this line are solutions that satisfy this equation. And everything along the red line are solutions that satisfy this equation. Therefore, x and y that satisfy both equations must be the point that simultaneously intersects by both of them. So that's the geometric meaning of what's happening when you are solving a linear system of equations. Of course, we solve it in a higher dimension. So we're also looking for some intersection. It's easier to see when you're in very low dimensions. And you can see that if you were to solve this, the result is 1, 1. And notice 1, 1 is the intersection. Okay? So that's what happens when you have a unique solution. There's one unique point where two lines intersect each other. In the case when there are no solution, it means that they can never, ever, ever intersect. The only way that's possible is if the two lines are parallel from each other. Then they can never, ever intersect. That's the case when there are no solutions. And the case where there are infinite solutions, right? It means that they are the exact same equation because the red line is on top of the blue line. So every single point is a solution. That's why there are infinite solutions. In higher dimension, then this is 3-dimension, then what we're doing is looking for the intersection of the plane. And then when we go even higher dimension, it becomes hyperplane, which is quite difficult to draw. Okay? For your exercise, you want to make sure you're able to do these two questions. What you want to do is solve the two linear system by hand. Use all the way, reduce it down to RREF. Once you solve it, then use SymPy to essentially verify if you got it right. Okay, I think I have the solution here, but I haven't updated the notation. So you're welcome to use the slide and check it out. Okay, well, I'll see you next class.